make a retainer bar thinner than they had in the past or
Yes.
thicker than they had in the past?
If you think of that picture of that whole bundle, when you're near the top and center of the bundle, your bend radius is much larger. You can have thicker bars. As you get to the edges of the bundle, because of the bend radius, you've got thinner bars. And in fact, for half of the retainer bars, they used thinner bars than they had previously used. And again, their mindset was that, previously this had been successful. It was not an operational item in their mind, so they didn't do the vibration analysis on the thinner bars.
Okay.
So it's related to the use of the thinner bars and the length of the thinner bars. Okay, so Unit 2 steam generator inspection results. Again, the Unit 2 steam generator inspection was largely done when we got into the Unit 3 results, so we went back in, and I should mention, to give you some perspective, we have done over 170,000 tube inspections between the two units. We're not talking about a weekend's worth of work here. We did months of tube inspections with these sophisticated probes and different probes to make sure we understood the indications, we characterized them properly, and went back in to confirm that we didn't miss anything. So with that background, so inspection results. First of all, and I stated this earlier, but to make it clear, Unit 2 actually met all the steam generator program requirements. When we shut down for an outage and do a steam generator inspection, whether it's the first cycle or several cycles down the road, we have to do an inspection of some sort, in this case 100% inspection, and confirm during the last operating period anything we found met the steam generator tube integrity requirements. That's part of the EPRI steam generator program. It is established by our technical specifications. We must meet that to confirm the steam generator is operated as expected. And Unit 2, in fact, did.
Hey, Tom, a quick question. Your initial exam of the Unit 2 steam generator, you did 100% exam with the eddy current probe. Based on Unit 3 experience, I think you went back into Unit 2 after extensive tube-to-tube wear on Unit 3. So you did more extensive evaluation of about 1,000 tubes, I think it was, with the rotating pancake.
Yeah.
Which is a more sensitive probe. And that's why I asked the sensitivity question earlier. The statement you just made that Unit 2 met all of the design criteria given the inspection results, is that still true given the rotating coil and the two indications that you're calling tube-to-tube wear at this time?
The Unit 2, my statement on Unit 2 meeting all the requirements, this was on the baseline inspection, which was both the bobbin and selected rotating probe, pancake coil probes. Just so you know, we went in with selected areas to look. And Unit 2, in fact, did meet all the program requirements. The two tubes we're going to talk about in a minute that had early indications of potential tube-to-tube wear, and I want to label that as potential, because they're just at the level of detectability, so we've treated them conservatively. Given that it's not a random phenomenon, that's one reason we decided not to proceed forward. It would still literally meet the program requirements, but we felt it was not prudent to move forward.
Okay, so you think it still meets program requirements even with
I'd have to go back and read the
indications?
program, but again, two indications well below the plugging criteria. We would identify them, we would evaluate them, decide, in terms of meeting the program requirements, it's a backward look to say was integrity maintained or challenged during the operating period. It in fact was maintained, not challenged during the operating period. So I would tell you, yes, it met the integrity requirements at the end of the operating period.
Okay.
Now, per the industry guidelines, a single tube pressure test. One of the retainer bar indications was deep enough and large enough. This is on one tube where the retainer bar wore against the tube. Was deep enough and large enough that we couldn't analyze that and decide simply to plug it. We had to actually go test it. This is how we demonstrate we met the steam generator integrity requirements. So when we find indications in a tube, no matter where they came from, we have analysis methods and the way to characterize it and say, if it meets certain requirements, it met the integrity requirements, I may elect to plug it or I may have to plug it, but I met the integrity requirements. If the flaw is such that I can't tell that by calculation, I have to test it. We had to test one tube in Unit 2, not related to tube-to-tube wear, related to retainer bar wear, and it in fact passed the test. Okay? Now, let's talk about tube wear in general. We found tube wear, and this is tube to anti-vibration bar wear. So those anti-vibration bar bars I've shown you, this is where some normal wear where the anti-vibration bar contacts the tube, and through normal vibration you get some wear. We found tube-to-tube support plate wear. I didn't dwell on it, but before, in the straight sections of tubes, there are 7 tube support plates which provide lateral support. There is some expected wear at those locations. We found retainer bar wear, and I've discussed that fairly extensively in answer to your question. And we found 2 tubes with potential indication of free span tube-to-tube wear. So let me talk about the first 2 types. We found more wear than we expected, more normal wear, tube to anti-vibration bar and tube-to-tube support plate wear. In brand new steam generators of this design and this material, we expected to find relatively little wear. We found significantly more wear than we expected. The wear is understood. It's due to random normal vibration. There is more of it than should be there. That relates to the adequacy of the support structure and the design, clearly. That wear is manageable on a going forward basis if that was all the issue, okay? Now, other units in the country, we've looked through this with the eyes of EPRI and our vendors. We're somewhat at the high end of the amount of wear after 1 cycle of steam generator operation. There's been a couple plants that are similar numbers, but we certainly are at the high end of that.
Hey, Tom, when you say the wear is manageable going forward, just expand on what you mean by that.
Well, the wear is understood. It can be predicted. It can be trended.
Okay, so wear rates can be
Wear rates can be predicted. We've
established.
got years of experience with it.
Okay.
The retainer bar wear is different. That was clearly a design flaw, which is unacceptable and had to be mitigated prior to restart, which is why we plugged 94 tubes in each of the steam generators to eliminate those tubes, so even if the retainer bar wears on them, they are not a source of leakage. And then the free span tube-to-tube wear, early indications potentially in Unit 2 on only 2 tubes in the 2 Echo 89, one of the 2 steam generators. I'm really going to get into that in depth as I talk about Unit 3. So what we did, the tube wear at anti-vibration bars and tube support plates, there were 2 tubes with wear above the 35% limit. As you are aware, in our technical specifications, when we have a wear flaw or a wear mark that is greater than 35% through the thickness of the wall of the tube, it has to be plugged. So there were 2 that were required by our program to be plugged. There were 2 more that were below 35%, but they were close enough that as we look at operating another cycle, we preventively plug those to be conservative and add safety margin. The tube to retainer bar wear, I've talked about that quite a bit. 4 of those were above 35%, but we preventively plugged another 100, and this is Unit 2 I'm talking about, 182 tubes just to take them out of service to ensure that that retainer bar problem did not affect the tubes. The tube-to-tube wear, again, Unit 2, we found 2 tubes, most likely caused by this in-plane vibration, which manifested itself severely in Unit 3. So we treated it as such. It was measured at 14% with the probes. It is probably a little less than that. That's a conservative sizing of that. It is well below the 35% limit, but again, not acceptable to keep in service. So they have been plugged. Additionally, and when I talk about the corrective actions later, we identified 321 other tubes between the 2 Unit 2 steam generators to preventively plug.
Hey, Tom, just clarify for me, you said, okay, so the 2 tubes, 14% wear at the realm of detectability, but unacceptable to keep those tubes. What makes that unacceptable? Just
Because
to be clear.
if they're due to tube wear, our experience out of Unit 3 and all of our work through the last 8 months shows the phenomenon in Unit 3 is unpredictable and it's rapid.
Okay.
So to contrast it, for people who are uninformed on the program, a 35% plugging limit, one of the things it's predicated on, if there is a wear indication below 35%, you can, as long as you can predict wear rates, you can justify leaving it in service and operating another cycle or till your next inspection. But it's got to be predictable, you got to have data, and it's got to be a phenomenon you understand and can predict. Tube-to-tube wear does not fall into that category. The 321 tubes we conservatively plugged between the 2 steam generators. We identified if the plant were to operate at 100% power, based on what we learned out of Unit 3, these would be susceptible potentially to the same phenomena occurring of this fluid elastic instability and excessive vibration, so we plugged them. Okay.
Tom, could you compare and contrast what you plugged in Unit 2 preventively versus Unit 3? Are they the same tubes? Is it a subset of the
It's a very similar set of tubes. And if you hold that question, Mr. Howell, I'm going to get to a tube map in a few minutes and I can come back to that. So now Unit 3. So I've kind of talked about Unit 2 and I've introduced Unit 3 quite a bit into it, but let me recap Unit 3. So after the January 31st shutdown, we went in and you start with which tube leaks. So we've got capability, once we shut down and cool down the unit and get into the inspection, to identify the leaking tube. We identified that readily. We then did the complete 100% inspection. The eddy current bobbin coil, the rotating coil examinations. That's done first of all with the leaking tube and the adjacent tubes to confirm the leak and characterize the nature of the leak. Then we did 100% full length of all tubes, just as we would have at the end of the cycle. Unit 3 had only run 11 months, nominally half of the full cycle. We did think of the U-bend portion of those tubes I talked about. We did a full U-bend exam around the retainer bars. Based on what we learned out of Unit 2 on the retainer bar vibration, we went and looked for the same issue in Unit 3, and we did confirm it. The same design problem with the retainer bar vibration. We then also did visual inspections from the secondary side, and we did specialty eddy current and ultrasonic examinations from inside the tubes to further gather data and understand principally the tube-to-tube wear phenomena, the nature of the wear, and the interaction with the tubes and the support structure. So steam generator inspection results. Stark contrast here. Unit 3 did not meet the inspection program, the performance requirements. As again, it's a backward look at the 11 months of operation. The tube leak itself, as well as the number of issues we found with tube-to-tube wear, did not meet the tech spec program requirements. So Unit 3 starts off very different than Unit 2 by the nature of the tube leak and by the nature of the tube-to-tube wear. Secondly, I described to you the one pressure test we did in Unit 2. One tube related to a retainer bar issue. Test in Unit 2 was done and passed. Unit 3, we had to do 129 tube tests, which is an extremely high number for any unit in an outage, and we had 8 tubes that did not pass. So they failed. So that tells us those 8 tubes would have failed structural integrity requirements. And there are 3 plateaus. One is an operational pressure, one is a main steam line break accident pressure, and one is an overall structural integrity. 3 failed at the main steam line break accident pressure, and the remaining 5 at the upper limit of structural integrity.
Hey, Tom, it might be useful at this point, we had one tube in Unit 2, and one of the steam generators that had to be pressure tested, and 129 total between the 2 generators in Unit 3. Can you just talk briefly about how it is determined to pressure test a tube?
Certainly, Mr. Lance. Yeah. And I alluded to this earlier, but basically when you do an examination of tubes with our electrical equipment, our eddy current equipment and our various probes, and you see some sort of wear indication or flaw in a tube, you've got to characterize it because it could be a challenge to steam generator tube integrity. It could be a challenge from a leakage or an integrity issue. So we've got to characterize the flaw and decide, does it have to be plugged? Does it hit the 35% limit or is it close? And whether it's above or below, we've got to characterize it and conclude that it meets the integrity requirement. If we cannot conclude that based on the shape and size of the flaw and do that analytically, we have to pressure test it. So in Unit 2, we had only one flaw that we felt we had to pressure test to conclusively demonstrate. In Unit 3, we had 129 tubes. We were not satisfied that analytically we could show they met the requirements, so we tested them. And in fact, 8 failed. We actually predicted those 8. Based on our calculations and flaw size, we said we would predict this would fail, and those 8 were in fact predicted to fail. So, quick summary, and I'm not going to dwell a lot on Unit 3. We've covered a lot of this. We did see wear at the anti-vibration bars. We saw wear tube support plates similar to Unit 2. We saw the same retainer bar wear, and we saw significant free span tube-to-tube wear. I will mention we see a difference in Unit 3 and Unit 2. Unit 3 ran 11 months, and even in the anti-vibration bar and tube support wear, what I characterize maybe as normal wear, only to a much greater degree than inspecting Unit 2, Unit 3 had even more wear and half the operating time. So Unit 3 is behaving differently than Unit 2. That is clear. And the free span tube-to-tube wear is very dramatic, but even as we look at our other wear indications, we see a difference between Unit 3 and Unit 2. Very quickly, because I want to get on really to the cause and the actions, to summarize, tube wear, retainer bars, we did the same thing we did in Unit 2. We understand that. all those tubes that are affected or potentially affected have been plugged. We did plug 3 tubes above the 35% limit at the anti-vibration bars. Significantly, we plugged 230 tubes above the limit at tube-to-tube support plate. Those are all related to tube-to-tube wear. What is happening there is those tubes that are vibrating excessively, we not only see it in the U-bend area, but they are vibrating against their tube support plates in the straight sections, and that's where that unusually high number comes from compared to Unit 2. And then tube-to-tube wear, 326 tubes between the 2 steam generators. So each Unit 3 steam generator has nominally 10,000 tubes. There's about 160 tubes in each that are affected by this excessive vibration, this excessive movement, the tube-to-tube wear, the tube-to-tube support plate wear, 326. And then we plugged another 292 tubes that would be susceptible at 100% power. Mr. Howell, I think this gets to the comparison you had asked about. Okay.
So you plugged roughly 200 more tubes in Unit 3 than in Unit 2.
Anticipating you might ask the question, we've done the math. And in Unit 2, we plugged a total of 517 tubes, either due to indications or preventatively as a conservative measure to add safety margin. In Unit 3, we've plugged 807 tubes. Now, I want everybody to know, we are not done with Unit 3. We've done enough work on Unit 3 to understand the effect on Unit 2, and that's where our efforts have been focused. So I'm not going to tell you tonight that I'm done with Unit 3 at 800 tubes.
Hey, Tom, one quick question. So 326 tubes plugged due to tube-to-tube wear, and precautionarily 292 more in Unit 3.
In Unit 3, that is correct.
Now, those 326, did they exceed the 35% value they were required, or that's just because
Some
they
of
had
them did,
tube-to-tube
some of
wear?
them did not. And I can give you a more detailed breakdown. If you look at the 230 tubes, they're a subset of that 326.
That was going to be my next
and
question.
those did exceed the 35% at the tube support plate levels.
Yeah, that's going to be my next question, is how the tube wear at the tube support plates was related to the tube-to-tube wear, and if they were the same tubes, different tubes.
Those 230 are a subset of 326, and what is happening is those 326 are vibrating excessively, and we're seeing the indications of that in the straight portions against the tube support.
Yeah, so my follow-up question then would be for the 2 tubes on Unit 2 that you characterized as having potential tube-to-tube wear, was there any indication of tube support plate on those 2 tubes that was wear that was a little more than what you saw
I
in
will
other
have
tubes?
to check the data. We inspected that, but out of the 20,000 tubes in Unit 2, those are probably the only 2 I didn't remember. So let me check that data and get back to you.
We do know that there weren't any, there were no tubes on Unit 2 that saw any wear at the tube support plates which required plugging.
Right.
Right, exactly.
We do expect to see some amount of what Tom has characterized as random wear driven by turbulence and normal vibration within the steam generators. But we can follow up with you, Mr. Lance, to get you the specifics on those 2 tubes.
We have got all that data.
And just for Mr. Howell's question, you had asked how does the overlay essentially of the Unit 2 preventive plugging compared to the Unit 3 tubes where we saw tube-to-tube wear. It was our intention to plug a very, very similar area on Unit 2, anticipating and with our conclusion that Unit 2 could be susceptible to the same phenomenon as Unit 3. So our intention was to overlay. And when Tom gets to his tube maps here in just a minute, you'll see that there is a specific localized region of the steam generators where we have that concern.
And in the material we submitted is with the Cal response, we submitted a lot of material that prevented plugging and the rationale for it, and the location is fully described. And again, we'll be glad to get into that in more depth.
So just so I'm clear, Mr. Dietrich, Mr. Polsano, you had roughly 620 tubes that were plugged in Unit 3 because of tube-to-tube wear. Is that
That is-
right? Either preventively or because they were affected in Unit 3.
That is correct.
And in Unit 2, you preventively plugged 321 tubes, with the difference being approximately 300 tubes.
That is correct.
Okay, and you say in the Cal response it provides the technical basis for that difference? Is
That's
that
right.
Okay,
yeah.
that's correct.
We identified a criteria, and it's summarized well in detail in the Cal response. In looking at Unit 2, if the plant were at 100% power, the tubes that would be susceptible to fluid elastic instability and this excessive vibration, and we elected to preventively plug all of those susceptible tubes. And we have our criteria laid out, And again, it's deeper than we're prepared to go in tonight, but we can easily take the staff through that. Okay, now with that background on inspection results and kind of a summary of the plugging, I want to talk about tube-to-tube wear. So as part of the methodology, if you think back to my earlier comments, so we've identified we've got this tube-to-tube wear occurring in Unit 3. So now what is physically happening and why is it happening? Steam generator cutaway, just to refresh us, we're going to be focused mainly on the upper part of the bundle, what we call the U-bend. I've annotated this as area of tube-to-tube wear. And think, one tube comes up in a U shape and comes out on the other side, hot leg to cold leg. So I'm going to show you a picture in a minute that talks about how these tubes are actually moving. Now this graphic, and I've exaggerated the tube, but this gives you a feel for how one of those long tubes, realize the very highest tube, 76 feet long, inlet to outlet. So this is a long, thin, very strong tube, but it's flexible. Okay? So the blue shape there would show you a tube, say, in a normal condition, with no movement, no deformation. The red shows you this the effect of this fluid elastic instability causing an in-plane vibration, causing this tube to move excessively, to vibrate excessively. So in this one, you can see what would be on the right side of the screen. The tube flexes or moves to the right as part of the vibration, and you can picture there are tubes above and below it. So you can picture this, if it moves far enough, it's going to contact the tube above it. And on the other side, it's contacting the tube below it. And then when that tube vibrates and flexes back the other way, picture that tube just vibrating back and forth. It's contacting tubes above over here, above on this side, and below on both sides. That is physically what's happening with the tube. Okay? So we plotted all of our indications out of the Unit 3 steam generators. And what we see here, this is just a schematic, I should just orient you. You're looking at a simple schematic of a cross-section of a steam generators. When you see things like O3H, O3C, O4, these are the tube support plates. So the tubes are straight in this portion. These are the tube support plates that provide horizontal support. Then the tube, if this were a tube, it bends through the U-bend portion, and these V-shaped things are the anti-vibration bars. Okay? So what is happening when these tubes flex back and forth, we are seeing the predominant number of these long wear scars due to tube-to-tube contact in this region of the U-bend and in this region. So going back to the previous slide, if the tube is moving back and forth this way, where would I expect to see the contact and the damage? And in fact, this correlates very well with where we are measuring the contact and the damage through all of our tube inspections. So this is part of the story now confirming, we understand how the tube is moving. It correlates with the actual measured damage that we see on the adjacent tubes in the steam generator. When I talk about 326 tubes between the two Unit 2 steam generators, this is where the predominant damage occurs. The other damage I haven't annotated would be those 230 things, whereas the tube vibrates, the top of the tube's moving, well, the straight portion is vibrating as well, and it's impacting the tube support plate. That's where those indications come from. Now, what I want to show you here, and this we'll start talking about an overlay. This is interesting. This is a little hard to understand, but this is actually a picture. We call it a tube map. This is a representation of the 10,000 tubes in one steam generator. So we're kind of in the primary side of the steam generator looking up at what's called the tube sheet, where all the tubes, either the opening is or the outlet is, the inlet or the outlet. And what this testing has shown, this darkened region is where, let's take, this is 3 Echo 88. I believe the number was 161 tubes affected by tube-to-tube wear. They are all clustered in a very tight cluster. So it's a very tight subset of tubes.
I just want to clarify, Tom, you said this was the whole steam generator. It looks like it represents half the steam generator. Is that, so it's like a hot leg side?
You're looking at the
or
hot
cold
leg side. Remember, the tube is a U-bend, so you're seeing the inlet to all 10,000 tubes. I have a companion picture that would show you the cold leg or outlet side. So this does represent all the tubes in a steam generator. It's just a certain view.
I see. Okay, thank you.
Yeah. Now, Unit 3, Echo 89 steam generator, very similar. Very similar in terms of pattern and very similar in terms of location. So, and what's important here is we understand the cluster, the pattern, and the location. This gives us clues to the conditions that are occurring that affect tubes in that region of the steam generator. And we're going to get to the thermal hydraulic conditions in a minute. Now, Unit 2. 2 tubes in Unit 2 between the 2 steam generators. That is a picture of the 2 tubes with potential tube-to-tube wear in the number 2 Echo 89 steam generator. Similar location, which led to our conservative decision to treat them as if Unit 2 was showing the early signs of phenomena at 100% power. And that, the clean picture, is the Unit 2 Echo 88 steam generator. We have seen no indication after multiple examinations in 2 Echo 88. But again, from a conservative standpoint and a safety margin standpoint, we feel it is important to treat Unit 2 as susceptible and propose the corrective actions we're proposing. Just going to give you a quick summary. We've talked about a lot of this. Unit 3 first, the number of tube-to-tube wear indications. Now, indications are different than the number of tubes. I can have multiple indications in one tube. Remember, I can have indications on either side of the U-bend. Okay? So one tube can have multiple indications. So in Unit 3, I have a total of 823 indications of tube-to-tube wear. They affect 326 tubes. The max depth is 100%. This, in fact, caused the leak. And we have a number of tubes that are well over 50% through wall, or tube-to-tube wear through wall depth. The longest length is 41 inches. That is an extremely long wear mark. Usually wear marks through normal random vibration are limited to the width of the anti-vibration bar that the tube's in contact with. These are extremely long. We had to do 129 pressure tests. That is an unusually high number for any site. We failed 8 pressure tests. That is an unusually high number. And the unit operated only 11 months on brand new steam generators. Unit 2 is clearly different based on results. We had 2 tubes with potential tube-to-tube wear indications, with 2 indications, 2 tubes. The maximum depth is about 14%, was about the limited detectability. The max length appears to be 6 inches based on our ability to characterize it. We had to do no pressure tests due to tube-to-tube wear, set aside the retainer bar issue. And we failed no pressure test, and it operated a full cycle of 21 months. So, based on all the work we've done, starting with what was the tube wear, what did it look like, where did it occur, how does the tube have to move, and with all the expertise we assembled to review this and develop this, we've identified the fluid elastic instability caused excessive tube vibration, and I didn't put up there, but in an in-plane direction, which is the unique phenomena that we've seen now in these steam generators in Unit 3. And that occurs when a tube is subject to fluid velocities above a critical value. In other words, the flow of water and steam past the tube is high enough, it's above a critical velocity that will start the tube to vibrate. And secondly, the support structure and the fluid is not damping the tube enough, so the tube vibrates unstably and with a high amplitude and allows it to contact it. That is the technical cause of the tube-to-tube wear. 2 key points, because these are important to corrective actions. It starts with adverse thermal hydraulic conditions. When you have high fluid velocity, that's what transfers energy to the tube. And that's where it's random, whether it's random vibration or this unique in-plane vibration, energy is transferred to the tube by the fluid. High localized void fraction. What does that mean? When I talk about void fraction or steam quality, I'm talking about how dry the steam is. The function of the steam generator is to boil water, turn it to steam to turn the turbine. And you want steam, but all that equipment at the top of the steam generator called moisture separators and steam dryers, because we want a certain amount of steam generated, but we don't want patches of very dry steam. We want to strip the moisture out in the very top of the steam generator. What's happening here, because of the adverse thermal hydraulics, we have high velocities. We also have localized patches of very dry steam. When you have very dry steam, the tubes are not effectively damped by movement through a water fluid, and there's not a water film between the tube and the anti-vibration bar. And that water film actually, the technical term through all the research is squeeze film damping. That water film actually helps to dampen the tube and prevent the vibration. When you have these adverse thermal hydraulics, the tube's excited and the vibration is not dampened. The other piece of this is the support structure, and this gets to a key difference between Unit 2 and Unit 3. Again, up until now, by the other manufacturers and MHI has been successful with this type of design in smaller steam generators before. The anti-vibration bars have been effective in controlling both out-of-plane and in-plane vibration previously, in MHI's experience and other vendors' experience. With this size steam generator, for whatever reason, this anti-vibration bar design was not effective, coupled with the adverse thermal hydraulics. So when the two combine, we have this localized area where this subset of tubes, nominally 160 tubes out of 10,000 each steam generators, were exposed to this and vibrated excessively, causing the damage.
Yeah, Tom, you said MHI was successful with the previous generators of a similar anti-vibration design. Would it be fair to say that, potentially those other generators just weren't challenged so much in the design because the thermohydraulic conditions were not the same?
It's hard to make a conclusive statement. We've done enough work with MHI and the other vendors. And MHI has supplied similar steam generators in Japan, elsewhere internationally, and one other set in the US, and they have been smaller. So it would appear to us that our thermal hydraulics, our fluid velocities and void fractions at 100% power, and that's a key, are higher than they have previously experienced before in their design. Okay?
Okay.
Mr. Hall?
Yeah, I just need a second to organize my thoughts. So, MHI, the vendor, when they designed the anti-vibration bars for your steam generators, it represented a departure from their previous design philosophy. In fact, they were trying to maximize dampening and minimize contact force, right? But I guess they didn't recognize, or it was not recognized, that by doing so, that it lowered the natural frequency of the tubes in the in-plane direction. Is that fair to say?
I won't say that conclusively without talking to MHI. I understand what you're saying. They have previously used this anti-vibration bar design specifically at the plant in this country, much smaller plant. They've used it elsewhere. In terms of their design philosophy, the zero gap, the contact force, without consulting with MHI, I can't state conclusively that that was their goal.
Okay. Well, clearly it was Edison's goal to minimize dings and dents in those tubes from the contact of the anti-vibration bars with the tubes. Right.
Our goal, our specification was a steam generator that would operate 40 years, very little tube wear, no tube leaks for a number of years, et cetera. In terms of how the designer does that to achieve those goals, we provide oversight. We rely on their judgment, their engineering expertise, and our oversight.
Hey, Tom, just to, Mr. Howell, to address your question, this goes back to some elements of what we were seeking in our replacement steam generators. The reason the industry, as you gentlemen know, the reason the industry has gone through a extensive and expensive and prolonged process of replacing steam generators was primarily due to phenomenon that occurred in the course of the lives of those steam generators that weren't fully expected when the steam generators were installed back in the original construction, 60s, 70s, into the 80s for us. That was primarily involved cracking of the tubes, which was driven by a chemical corrosive attack. But also, one thing that's important, very important to note and to understand, is that at San Onofre, we were also seeing on the original steam generators a significant amount of wear. Not just the cracking, but we were seeing a significant amount of wear. And on one of the units, I recall it being Unit 2, the steam generators were actually approaching the end of their useful life because of the tube plugging that we were having to do due to wear on the tubes, not just the cracking. So in our replacement steam generator design and specification, our intention was to minimize wear because that was, in fact, what had driven us to the replacement requirement. And in our desire to install components that we knew could operate reliably for the operating life of the plants and be able to safely, correctly, efficiently provide electric service to our customers and ratepayers, we were seeking to resolve the issues that were requiring us to replace the steam generators. So our desire was to minimize wear. We also addressed the generic or general industry issue of the cracking, and that came through the replacement of the tube material, going from what was called alloy 600 Inconel to the alloy 690. Right. So a little bit differently maybe than other steam generator replacements of the industry, which were primarily driven by the corrosion cracking. The San Onofre replacements were driven by wear as well. And so that's why this wear focus in our specification to the steam generator designers was so important to us.
We understand what has occurred, fluid elastic instability, excessive vibration, and we understand what causes it in terms of adverse thermal hydraulics and the support structure. And then I'm going to move on to our corrective actions for Unit 2. Mr. Lance?
I keep hitting the button here. Go ahead, Art.
Well, when you say support structure, you mean because there was a lack of contact between the AVBs and the tubes?
I'm starting with the fact that the support structure was ineffective in damping vibration. Whether it was lack of contact or lack of sufficient contact force, some of that is yet to be concluded. Okay? Those are some of the early indications that the zero contact design, and in fact, if we think about it, Unit 2 is very different than Unit 3. Unit 2 support structure was much more effective than Unit 3 with the same thermal hydraulics. The thermal hydraulics are the same for all 4 steam generators, yet Unit 3, after only 11 months, has significant damage. Unit 2 maybe has 2 indications.
But the contact force in Unit 2 has been probabilistically estimated to be twice that of Unit 3.
Yes, that's part of the difference. So as we continue to unravel this with MHI and do deeper technical work and causal analysis work, the support structure is more effective in Unit 2. Our testing and MHI's testing and the analysis well of all our experts indicates there is both more contact and contact force between the anti-vibration bars and the tubes in Unit 2 than exists in Unit 3.
So just so we're clear, I think you know where I'm going with this. The point is that these anti-vibration bars were designed purposefully to have zero contact force. And yet now the conclusion is, after the event occurred, the tube leak, that it's because of that lack of contact force that contributed to the phenomenon of fluid elastic instability.
I think that's a fair statement at this point.
Well, I think what's important to point out here, just let me help with a little bit more information, and it does get very technical, and it's not our intention to lose people in this discussion. But Tom had previously mentioned, Mr. Howell, the squeeze film damping. And although the steam generators were designed that in a hot operating condition, there would be contact, but there wasn't a specific specification for the amount of force that would exist between the anti-vibration bar and the tube. The intention was, and the technical analysis and science behind fluid elastic instability and steam generator design has showed the effectiveness of this squeeze film damping. And so what the design counted on was for there to be a film of water there. And because that film of water was there, it would in itself provide enough resistance in addition to the essentially zero gap, although no force, to provide resistance for the tube moving. And those are the things that we could continue to study in our root cause. What it's very important to point out, and I don't mean to jump ahead, but we are talking very specifically about all of these thermohydraulic conditions that exist at 100% power. And this is the fundamental reason that in our proposed confirmatory action letter response, our desire is to only operate the unit at 70% power. And Tom, we have information for you here in a few minutes, what will show the improvements in the thermal hydraulic conditions, the fact that you reduce the velocity and you improve the amount of moisture in the steam to restore this squeeze film damping, even on Unit 2, where we didn't see the tube-to-tube wear. So I do think we get to this point. There is a tremendous amount of science and research behind fluid elastic instability, as I'm sure you're aware, Mr. Howell, and we have learned a lot working with the renowned experts in the industry, some of the most published professors and other folks in the world. But we look very much forward to that discussion around some of these very specific but important aspects of steam generator design.
I appreciate that. So you talked about how the reduction of power will improve the thermal hydraulic conditions. That is one of the big contributors to the fluid elastic instability, but you also talked about the support structure. And so as part of the discussion, I imagine you're going to also tell us how that factors into operating, the justification for operating at 70% power.
I'll be glad to address that. And that is fully described in our confirmatory action letter response, the role of the support structure. And again, Unit 2 has a more effective support structure than Unit 3.
Yeah, if I could just tack on to that. You keep talking about an adverse thermohydraulic condition, and that is the kind of the precursor that imparts the energy to the tubes to allow an inadequate support structure to allow excessive vibration to occur. My question, you're going to talk about 70% power as a reduction in those thermal hydraulic conditions. In your Cal response, do you discuss other factors in the design of these generators that ultimately created this adverse thermohydraulic condition? You're saying it can go away if you go to reduced power, but why is it there in the first place? And what aspects of the design created that condition? That's my question.
Okay. The current Cal response, and we'll get into this over the next several weeks as we get into the technical detail, describes what occurred. I'm sorry? Is the mic on? Okay. Anyway, the Cal response describes the condition, describes why it occurred, describes the role of the thermal hydraulics and the fact that they were underpredicted, describes the contact force problem that occurred. At that point, MHI's root cause has not been completed, so as we look at longer-term actions, there's more technical work to do to better understand the contact force assumptions, the role of contact force, and whether, in the end, it's the number of tubes in a physical space that created the thermal hydraulics, as well as the role of the contact force.
Yeah, I understand. To do a full repair, restore the generators to 100% power,
Right.
You'll have to be able to understand how to bring a thermohydraulic condition back in line with something normal that doesn't create this excessive
Right.
force on the tubes. But I think it is important to understand what the contributors are so that we can understand how effective the 70% power reduction is.
And I
why
think you'll
that
find
is
in our Cal
reliable enough.
response, we've discussed the contributors adequately.
Yeah, thank you.
So,
Well, I think, Tom, your next point, we're going to get into the roles of the
Right.
thermal hydraulic code and talk about specifically how the thermal hydraulic code and some of the issues associated with the thermal hydraulic code factored into this situation.
Yep.
And there is specific information in our confirmatory action letter response which shows the velocities within our steam generators at 100% power, our velocities at 70% power, and experience within the nuclear industry today of similarly designed steam generators at the same velocities that we are proposing in our operation at 70% power. And it shows that those steam generators are stable. Those steam generators don't see this in-plane fluid elastic instability. So certainly more than willing to talk about all aspects of that.
Yeah, I think, Mr. Dietrich, the reason why we're asking is, you all have defined the phenomena as adverse thermal hydraulic conditions and support structure unable to control the resulting vibration.
correct.
And so part of the, I don't know if it's part or all, of the action that you're using to justify operating at 70% power is the actual power reduction, and you're no longer worried about the support structure performing a design function that it was never intended to perform, which is in-plane stability for those tubes. Or you still